Okay, so now we have another example where we once again want to find the concavity and points of inflection. This time the function's a little bit more complicated. Here we have a rational function 5x over x squared plus 4. So we begin, though, since we're talking about concavity, we have to find our second derivative. So first we find our first derivative. That would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now before we go forward trying to find the second derivative, let's do a little bit of simplifying. So we distribute the 5 through, get 5x squared plus 20, and 5x times the 2x, we get minus 10x squared. That's all over x squared plus 4 quantity squared. So we take that result now, and we can simplify just a little bit more. We have a 5x squared and a minus 10x squared. So we can simplify that to get 20 minus 5x squared. So again, 5x squared plus 20 minus 10x squared. We combine like terms, we get 20 minus 5x squared. So that's our first derivative, and now we want to differentiate that. So we take the bottom, x squared plus 4 squared, times the derivative of the top, which would be a negative 10x, minus the top, times the derivative of the bottom. Well, let's look at the derivative of the bottom for a moment. We're differentiating x squared plus 4 quantity squared. So it's a composite function, so we're going to need to use the chain rule. So u would be the inside function, x squared plus 4. F would be the outside function, u squared. Then that would be 2 times u, right, by the chain rule. But u is just x squared plus 4. So it would be 2 times x squared plus 4 to the first, times the derivative of u, which would be 2x. So we can take that expression and simplify it and put that into our problem. So that would be 4x times x squared plus 4 to the first, which would just be x squared plus 4. And that's all over our bottom thing squared. So x squared plus 4 squared squared, but x squared plus 4 squared squared is the same as just x squared plus 4 to the 4th power. Okay? And now at this point, we have some simplifying to do. As very often happens when you're dealing with a derivative involving a composite function, you're going to have something to factor out. And in this case, we have that x squared plus 4 squared and that x squared plus 4. So we factor out an x squared plus 4, our common factor. Yes, there are other common factors as well that we can take out, but we're really not worried about those. Okay, this is just the simplifying type of factoring. So we pull out that x squared plus 4, and when we do that, you may want to pause things to catch up here. In the first part, when we take out the x squared plus 4, we'd be left with just a negative 10x and an x squared plus 4 to the first power. In the second part, when we take out the x squared plus 4, we're left with just a minus 4x times 20 minus 5x squared. And then that's all over our denominator raised to the 4th power. As you're watching this video, if at any time you need to pause it, please pause it to catch up. Now I can take that x squared plus 4 and cancel it with the 4 down there. Alright, cancel out with the 4th power. So that actually leaves me now with my quantity, negative 10x times x squared plus 4 minus 4x times 20 minus 5x squared all over x squared plus 4 to the 3rd power. I'll just pause for a second to let you kind of digest what we've done so far. At this point now, we're going to jump to our next page. So I have that same expression, just duplicate it. And now I want to start simplifying. So again, same expression that we had before, just taking that and duplicating that. And now we can start simplifying a little bit. So negative 10x times x squared plus 4 would be a negative 10x cubed minus 40x. And then we have the minus 4x times 20 minus 5x squared will be minus 80x plus 20x cubed. Be careful, that's a negative 4x and a negative 5x squared. So that's going to be plus 20x cubed. And that'll all be over the bottom to the third power. Okay, we have a few like terms here that we can combine. We have a negative 10x cubed and a 20x cubed. So we put those together. And let me, hold on, went a little too fast there. We put those together. And we have 10x cubed. And then we have a minus 40x and a minus 80x. So those two will go together. The minus 48 and the minus 80x will go together to be minus 120x. So we're going to have 10x cubed minus 120x. All right, now, all that time just to get the second derivative. See what I mean by when the problem's any bit of complexity, there's work in finding that second derivative. Now that we finally found the second derivative, we can ask the question, when is it 0? When is it undefined? Well, this is never going to be undefined. The only time a fraction like this will be undefined is when its denominator is 0, but that denominator can never be 0. So we ask the question, when is the numerator 0? That would be 0 when 10x cubed minus 120x is equal to 0. We factor out an x. Actually, we factor out a 10x. We get 10x times x squared minus 12 equals 0. Take a moment and solve that. You'll get that x has to be 0, and that x is plus or minus the square root of 12. But square root of 12 can be simplified to 2 square roots of 3. And for reference now, as we're testing values, 2 square roots of 3 is roughly negative 3.46. So we've now determined when our second derivative is 0 and when it's undefined. So we then graph those on a number line. And then we're going to test values of the second derivative because, once again, that's what we want to know the sign of so we can talk about concavity. So we pick some value smaller than negative 2 square roots of 3 or negative 3.46. So perhaps we do f double prime of negative 4. And if you evaluate the derivative, second derivative, at negative 4, you're going to find out that it's negative. Then we want to pick something between negative 2 square roots of 3 and 0. So I believe I picked negative 1. And you're going to find that the second derivative there is positive. Pick something bigger than 0. I'll pick 1. We're going to find that the second derivative is negative there. And then pick something bigger than 2 square roots of 3. I happen to pick 4. We're going to find the second derivative is positive there. You really should pause the video at this point in time and actually evaluate that yourself. And instead of picking those values, maybe you want to pick your own, just to see that the sign of the second derivative is as we've stated it here. Once we know the sign of the second derivative, we can then list out when it's concave up. It'll be concave up in those intervals where the second derivative is positive. It will be concave down in those intervals where the second derivative is negative. So that takes care of the concavity part of the problem. What about those points of inflection? Well, each of those points there are points where the concavity does change. Now if they happen to actually be points on the graph, then we're good. We'll have concavity, or we'll have points of inflection at those points. So to find out if there are points on the graph, let's evaluate the function. So I start by evaluating at negative 2 square roots of 3. When I plug negative 2 square roots of 3 into the original function now, because we want to determine when, what the point is on the graph of the original function, I get the following, and upon simplifying, you get negative 10 square roots of 3 over 16, or negative 5 square roots of 3 over 8. So that gives us 1 point of inflection at negative 2 square roots of 3 and negative 5 square roots of 3 over 8. And then we check our next point, which, to save myself a little bit of writing, I'm going to jump to the 2 square roots of 3. When I plug in 2 square roots of 3 into the original function, I get the following. And upon simplifying, I get 5 square roots of 3 over 8. 5 square roots of 3 over 8. So the point 2 square roots of 3, 5 square roots of 3 over 8 is also a point of inflection. And then the last one to check is 0. If you plug 0 into the original function, you get 0. So that 0, 0 is also a point of inflection. Again, I went through those pretty quickly, so you may want to pause and kind of check that yourself to see that that is the result that you get. So it's concave up between negative 2 square roots of 3 and 0, and 2 square roots of 3 and infinity. It's concave down between negative infinity and negative 2 square roots of 3, and then again between 0 and 2 square roots of 3. Let's take a look at the graph of our function, and let's see. I've highlighted here in red those places where the graph is concave down. Now it's kind of a little hard to see on the tail end there. If you zoom the graph out a little bit more, you can see it better, but when I did that, the image didn't show things as nicely for other things. So I kind of had to shorten the graph down a little bit, but it does actually start curving into that concave down like a frown shape there below negative 2 square roots of 3. And so that's where it's concave down, there in red. And then it's concave up like a cup, where I've now marked in blue. And you can kind of see that it is starting to turn down a little bit there as you pass that point, 2 square roots of 3. As you pass those points, 2 square roots of 3 and negative 2 square roots of 3, which again are about negative 3.46. Okay, and then we have our points of inflection, those points there where the concavity is changing. Okay, this video did turn out to be a little bit long, but remember, a lot of the work was in finding that second derivative. Once we found that second derivative, the rest of the problem kind of flows from there. Hopefully this helps you as you're trying to tackle these problems with concavity and points of inflection. Good luck until next time.